Hi, I am Sanjay Patel. In this video, we are going to learn some more formulae of finding nth derivative of some standard functions. In the previous lecture, we have derived the two formulas for finding the nth derivative. The first one was y is equal to e raised to ax plus b. Then its nth derivative, that is yn, is a raised to n into e raised to ax plus b for every n belongs to n. And the second formula what we have derived as the second theorem as y is equal to a raised to lx plus m, then nth derivative yn is say L raised to n into log of a to the base e raised to n into a raised to lx plus m, and this is also for every n belongs to n. Now in this lecture we are going to derive some more formulas, and let us consider that as our third result. I will call it theorem number 3. Okay, what we are going to prove is this: if y is equal to sine of ax plus b, where a and b are some constant, or you can say a and b are some real numbers, then yn is equal to sine ax plus b, yn is equal to a raised to n into sine ax plus b plus n times pi by 2 for every n belongs to n. So you want to derive this as a theorem. The same result is there if you replace sine by cos. That means if y is equal to cos of ax plus b is given, then you can write down the nth derivative by just replacing the word sine by cos. Yn is equal to a raised to n cos ax plus b plus n pi by 2. So let us prove. And we have discussed in our previous video that all the results of this successor differentiation we are going to prove using the principle of mathematical induction only. So whatever is to be proved, in this case we have to show that yn is equal to a raised to n into sine ax plus b plus n pi by 2 for every n belongs to n. So that thing we are going to take as our statement Pn. So let us consider P of n as yn is equal to a raised to n into sine ax plus b plus n times pi by 2. Okay, and in the induction, the first thing what we do is we check the result is true for n equal to 1. So for n is equal to 1, means I have to show that y1 is equal to a raised to 1 sine ax plus b plus 1 into pi by 2. Okay, so here we start with this thing. We have the given function y is equal to sine ax plus b, and you want to find y1. That means you want to find first derivative. So differentiating this with respect to x, we get y1, that is dy by dx, as a into cos ax plus b. Derivative of sine theta is cos theta, and again we will differentiate this theta, that is ax plus b, and the derivative of ax plus b is a. So you will get this thing. Now we want to show that this y1 here is in this form. So we should convert this cos function into sine function, and we have many trigonometric identities or formulas using which we can write this cos in terms of sine. You know that cos theta is equal to sine pi by 2 plus theta. So I can replace this cos by sine of ax plus b plus pi by 2. Okay, because we know that sine pi by 2 plus theta is equal to cos theta. Okay. This is nothing but our P1. See, for n equal to 1, we are getting the same thing what we require in this statement. Putting n equal to 1, we get y1 is equal to a raised to 1 sine ax plus b plus 1 into pi by 2, that is pi by 2. So the conclusion is, therefore, I can say P of 1 is true. P of 1 is true. Now we assume that P of k is true. Okay, so suppose Pk is true. That is I can write Pk as say yk by putting n equal to k in this, where k is some fixed natural number. So a raised to k into sine ax plus b plus k into pi by 2. And let us call this as result 1 always. Okay. So we assume that this result is true for n equal to k. And now we want to prove that P of k plus 1 is true. That means the result is true for k plus 1 also. And for that, let us consider the next derivative of this yk. Yk means the kth derivative of y with respect to x. So we differentiate the result number 1 with respect to x, both the sides. With respect to x on both the sides. So what we get is yk plus 1, because derivative of yk is the next derivative, that is yk plus 1. Here this a raised to k is constant in this, so we keep it as it is. And derivative of sine of something, that is sine of theta, derivative is cos theta. So first I will write that cos of ax plus b plus k into pi by 2, and derivative of ax plus b plus k pi by 2, where b is constant, k into pi by 2 is constant, so its derivative is 0. So what remains is only a. So this into a will be there. Okay, and this we can write as a raised to k plus 1, and this cos theta I want to write in terms of sine theta. So I can use the same formula, this one, sine pi by 2 plus theta is cos theta. So this cos theta you can replace by sine pi by 2 plus theta. We do the same process here. So we write sine of this, I am writing as it is, which is our theta, k pi by 2 and plus pi by 2. So what we are using is this formula again. Cos theta we can write as sine pi by 2 plus theta. So this gives us yk plus 1 is equal to a raised to k plus 1 into sine ax plus b plus, now adding these two, k pi by 2 plus pi by 2 gives you k plus 1 times pi by 2. Okay, this suggests this says that pk plus 1 is true, because this is the required result. By putting n equal to k plus 1, you can check here. This is a raised to k plus 1 sine ax plus b plus k plus 1 times pi by 2, and we have obtained the same thing. So thus P of k plus 1 is true, and we always write, therefore pk implies pk plus 1 is true. Assuming the truthness of pk, we have proved that pk plus 1 is also true, and therefore the statement Pn is true for every n belongs to n. Okay, so what is proved? That is yn is equal to a raised to n into sine ax plus b plus n into pi by 2 is true for every n belongs to n. Okay, so we have proved this first theorem of today's lecture, that if y is equal to sine ax plus b, then yn is equal to a raised to n sine ax plus b plus n pi by 2. Now just replace the word sine by cos at these two places, and what we get is our next result, that is theorem number 4. So let me write as theorem number 4, and it is if y is equal to cos of ax plus b, where a and b are constant, then prove that the nth derivative yn is a raised to n into cos ax plus b plus n into pi by 2 for every n belongs to n. Okay, let us prove this. So again, as usual, we can consider the thing which is to be proved, because it is to be proved for every n belongs to n, as Pn, because we want to use the principle of mathematical induction every time in this. Yn is equal to a raised to n into cos of ax plus b plus n into pi by 2. Okay, then the first step, we prove the result for n equal to 1. We check it is true or verify it is true for n equal to 1. So here we have the given function y is equal to cos of ax plus b, and we differentiate this with respect to x to get the first derivative dy by dx, that is y1. Derivative of cos theta is minus sine theta, so we get minus sine ax plus b, and derivative of theta, that is ax plus b, with respect to x is only a. But we want to write this in terms of cos, because we want p1 is true. P1 is true means y1 is equal to a raised to 1 into cos ax plus b plus pi by 2. So this I can rewrite as a into cos of say ax plus b plus pi by 2, because we know that this cos pi by 2 plus theta, cos of pi by 2 plus theta is equal to minus sine theta, correct? Because pi by 2 plus theta is in the second quadrant where the cos function is negative, so we get minus sine theta here. So this says that P1 is true, therefore P1 is true. Now let us assume that Pk is true. So suppose P of k is true, and that is we have yk, just putting n equal to k here, we get P of k. So I am writing it like a raised to k into cos of ax plus p plus k into pi by 2, and let us call this as result number 1. Okay, now we want to derive pk plus 1 from pk, and pk plus 1 means we have to show that yk plus 1 is equal to a raised to k plus 1 into cos of ax plus b plus k plus 1 times pi by 2. So we need k plus 1 everywhere here, and yk plus 1 means the k plus 1th derivative of y. And you know, if you differentiate yk, you will get the next order derivative, that is k plus 1th order derivative. So let us differentiate this with respect to x. So for pk plus 1, we differentiate result number 1 with respect to x on both the sides. Of 1. Okay, so we get yk plus 1 is equal to, this a raised to k is constant in multiplication, so we keep it as it is. This into derivative of sine theta is derivative of cos theta is minus sine theta, so minus sine ax plus b plus k times pi by 2 will be there, and derivative of this theta, which is function of ax plus b plus k pi by 2, this derivative will be only a, because b and k pi by 2 are constants, so we get simply a into 1, that is a. And this we can rewrite as a raised to k plus 1 into, and minus sine theta as here as here we can write minus sine theta as cos pi by 2 plus theta. So these I can replace by this thing, cos ax plus b plus k into pi by 2 plus pi by 2. So again I am using this fact, minus sine theta is same as cos pi by 2 plus theta, or cos theta plus pi by 2. So this gives us yk plus 1 is equal to a raised to k plus 1 into cos of ax plus b plus k plus 1 times pi by 2. And this says that p of k plus 1 is 2. This was the required result. So the conclusion is, therefore p of k plus 1 is true. So what we have proved is this: pk implies pk plus 1 is true, and therefore p of n is true. P of n is true for every n belongs to n. Okay, this you must write in all the theorems at the end after proving the result by induction. So that is yn is equal to a raised to n into cos ax plus b plus n times pi by 2 for every n belongs to n is also proved. Okay, so we have proved two theorems. The next is a combination of the two functions. One is exponential and other is say the sine or cos, and that is also very important result. So let us consider as our theorem number 5. If y is equal to e raised to x into, or rather e raised to ax, let us call it e raised to ax into sine of bx plus c. So it's a product of two functions, one is e raised to x, another is sine function. So if y is equal to e raised to ax into sine bx plus c, then prove that its nth derivative yn is equal to r raised to n into e raised to ax into sine bx plus c plus n into phi for every n belongs to n. Here two new symbols are there. One is r and other is phi. And what is the meaning of r and phi in this? So that is given by where r is equal to square root of a square plus b square. So if you have this kind of function, y is equal to e raised to ax into sine bx plus c, then the coefficient of this e raised to this coefficient of x here in the power of e, that we take as a, and the coefficient here in the sine function, this argument, we take as b, coefficient of x. So then we find r is equal to square root of a square plus b square. And after finding r, we can find the value of phi, that is this phi, using the formula or the relation a is equal to r into cos phi and b is equal to r into sine phi. Okay, and this theorem we can also rewrite in a different way. I mean, we can write this yn by this way also. If y is equal to e raised to ax into sine bx plus c, then we have yn is equal to, what we can do is, instead of writing this separately, we can put the value of r and phi in this result. So I can write, r is a square plus b square raised to 1 by 2, and then raised to n is also there here. So r raised to n will be a square plus b square raised to 1 by 2 raised to n, that gives us n by 2, into sine of bx plus c plus n into phi. Okay, now what is this phi? How we can derive phi? we can derive phi from these two equations. Okay, so you can take tan phi, and tan phi is equal to b upon a. If you take b upon a, you will r will be cancelled and you get tan phi, and so phi is equal to tan inverse b upon a, and this is to be proved for every n belongs to n. Okay, so the same result we can write in these two different ways. Now let us prove this. So proof of this, first of all, let us consider P of n. What is P of n? P of n, I will take this, yn is equal to r raised to n into e raised to x into sine bx plus c plus n phi. So let us take Pn as yn is equal to r raised to n into e raised to ax into sine bx plus c plus n into phi. Okay, suppose this is asked, then you can first take r is equal to a square plus b square raised to 1 by 2 and take phi is equal to tan inverse of b upon a. Okay, now the first step here is we have to show that p1 is true. So consider n equal to 1. Let us take n is equal to 1 here, and n equal to 1 means we have to find y1. So from y is equal to, we have the function y is equal to e raised to ax into sine bx plus c. This is not directly, we can say as in the previous results, we have to do some simplification here. I want y1, so differentiate this with respect to x. Differentiate both the sides with respect to x. So what we get is y1, we get y1 is equal to, now for differentiating this, there are two functions, one is e raised to x, other is sine bx plus c. So we have to use u into v rule. So u into v, that is, I can keep say v as it is and find the derivative of e raised to ax. So derivative of e raised to ax is a into e raised to ax, and this second function sine bx plus c I am keeping as it is. So this is my u and this is v, plus now e raised to ax as it is, and derivative of sine theta is cos theta, that is cos bx plus c, and derivative of bx plus c is b. Okay, now this I can rewrite as by taking e raised to ax as a common factor, e raised to ax into say sine bx plus c into a plus cos bx plus c into b. Now what are a and b? That is given to us in the statement of the theorem, where a is equal to r cos phi and b is equal to r sin phi. So I will substitute the values of a and b in this. So I can write, say, let us put a is equal to r cos phi and b is equal to r into sin phi. So therefore we get y1 is equal to e raised to ax into sin bx, this r cos phi into, sorry, let me write this way, sin bx plus c into r cos phi plus cos bx plus c into r sin phi. Just we are putting the values of a and b only here. Okay, so this gives me, again you can see here r is common in these two places, so we can rewrite this as y1 is equal to say r into e raised to ax, r into e raised to ax into sine bx plus c into cos phi plus cos bx plus c into sine phi. Now you can immediately point out that this bracket quantity is nothing but the formula of sine alpha plus beta. If this is alpha and phi is equal to beta, sine alpha cos beta plus cos alpha sine beta is nothing but sine of alpha plus beta. So this gives me y1 is equal to r raised to 1 into e raised to ax into sine of bx plus c plus phi. Okay, and this is nothing but our p1. You can check by putting n equal to 1 here. y1 is r raised to 1 into e raised to ax into sine bx plus c plus 1 into phi. So this says p of 1 is true. So therefore, p of 1 is true. Okay. Now let us take the next step as assume the result is true for n is equal to k. That is, suppose p of k is true. Suppose p of k is true. And that is, we have yk is equal to r raised to k into e raised to ax into sine of bx plus c plus k into phi for some k belongs to n. Here k is any number, but it is fixed. Now we differentiate this result to get pk plus 1 or say yk plus 1. So let me write this way. Differentiate result number 1 with respect to x on both the sides. So we get yk plus 1, derivative of yk will be yk plus 1, and now we have to differentiate this right hand side. In this right hand side, this r raised to k is constant, so that I will keep as it is in multiplication, and for this remaining two things, that is, one is a function e raised to x and other thing is the function sine of bx plus c plus k phi. So here we apply again u into v rule, and I will write here it as derivative of e raised to ax first as a into e raised to ax, and this sine theta as it is, that is sine of this bx plus c plus k phi as it is, and plus e raised to ax as it is, and derivative of sine theta is cos theta, means sine of this thing is cos of this thing, and derivative of bx plus c plus k phi, where c and k phi, these are constants, derivative of this will be 0 and derivative of bx is b only. So this I can write as cos of bx plus c plus k phi into b, okay, like this. And now you can see in these two terms e raised to ax is common. Okay, so I am taking e raised to ax, these two things, as a common factor outside and write like this, r raised to k into e raised to ax, and we'll write the remaining things as sine bx plus c plus k phi first into, I will write this a which is there, plus cos bx plus c plus k phi into b. Okay. Now to convert into the required form in this form, what we write is values of a and b. You know what is the value of a and b? So I can say, putting a is equal to r into cos phi and b is equal to r into sin phi only in this square bracket, we get yk plus 1 as r raised to k into e raised to ax as it is into sine bx plus c plus k phi into r cos phi plus cos bx plus c plus k phi into b is equal to r sin phi. We are writing here. So I am putting the values of this a and b only at these two places. Okay. So this gives me yk plus 1 as, see, in this expression, this r is a common factor which I can write outside, and that makes this r is to k as r is to k into r as r is to k plus 1 as above, and e raised to ax as it is. And this gives me sine bx plus c plus k phi into cos phi plus cos bx plus c plus k phi into sin phi. This is again sine alpha plus beta. You can call this as alpha and this as beta. So sine alpha cos beta, and here this is cos alpha sin beta, and that is nothing but sine alpha plus beta. Okay. So that gives me yk plus 1 is as in the required form as e raised to ax into, move this now, into sine of this alpha, that is bx plus c plus k phi, and plus beta is phi. So this gives us k plus 1 times phi in this bracket. So this gives us, final step, yk plus 1 is equal to r raised to k plus 1 into e raised to ax into sine of bx plus c plus k plus 1 times phi. So thus pk plus 1 is true. Pk plus 1 is true. And therefore the final conclusion here is pk implies pk plus 1 is true. Pk implies pk plus 1 is true, and therefore this p of n is true for every n belongs to n. Okay, for every n belongs to n, and that is nothing but yn is proved. That is yn is equal to r raised to n e raised to ax into sine bx plus c plus n into phi for every n belongs to n. Okay, and we have a similar result, exactly same way we can prove the result for cos function also. So this theorem 5, where we written it as phi is equal to e raised to ax into sine bx plus c, just replace sine by cos here as well as here, then it also remains true. So let me write it as theorem number 6, and I leave it to you to prove it yourself. It is on the same line, as you know, very simple, say, differentiation. You can prove this on your own. So theorem number 6, if y is equal to e raised to ax into cos of bx plus c, then prove that yn is equal to r raised to n into e raised to ax into cos of bx plus c plus n into phi for every n belongs to n. Okay, where a is equal to r cos phi, b is equal to r sin phi, and r is equal to square root of a square plus b square. So first we must find r value, then we can find the value of phi from these two relations. A is equal to r cos phi and b is equal to r into sine phi. Okay. And same way we can write this by putting the value of r here in a different form as if y is equal to e raised to ax into cos bx plus c, then we can write yn is equal to yn is equal to a square plus b square raised to n by 2, because I am putting the value of r is equal to a square plus b square raised to 1 by 2 here into e raised to ax into cos of bx plus c plus phi is given by tan inverse of phi. Tan inverse of b upon a. Phi is given by tan inverse of b upon a, because if you take b upon a, you will get tan phi, and therefore phi is equal to tan inverse b upon a for every n belongs to n. Okay. This I leave it to you. The proof is exactly same as theorem number 5, only the function is changed. Okay. Now we'll see some simple one or two examples based on this, these 4 theorems. So let me take as say example number, say one example only. We'll take more practice in that say later on. Consider y, say y is equal to, suppose if I am given say sine x into cos x. Let me take a very simple example. Then find the value of yn and say yn of 0. Okay. So first of all, this sin x into cos x, such function nth derivative we have not obtained. What we know is nth derivative of sin x or cos x or e raised to ax into sine or cos. These are the only 4 results we have derived in the last 2 lectures. So what I am going to do is I will convert this y is equal to sin x into cos x into the known formula. And we know very well that 2 sin theta cos theta is sin 2 theta. So that converts into only sine function. So we can write y is equal to 1 by 2 into 2 sin x into cos x. So that gives us 1 by 2 times sin 2x. Okay, see 1 by 2 is constant in multiplication, so it will not create any problem. So the nth derivative, because we have the formula for finding nth derivative, say let me write here, if y is equal to sin ax plus b, then we know the formula for yn is sin ax plus b plus n pi by 2. Okay, so here in our case sin 2x is only there, so this value 2 is the value of a, so putting a equal to 2 and b is not there, so putting b equal to 0, what we get is yn is equal to 1 by 2 times sin 2x plus n times pi by 2, sin 2x plus n times pi by 2. Okay, so this is the answer, and using this formula you can find the derivative of this function y is equal to sin x into cos x for any value of n belongs to n. Means you can find 100th derivative or say 10,000th derivative using this answer. But we are required to find yn 0 also. That means the value of the derivative yn at x equal to 0, or nth derivative value at x equal to 0. Remember, this can also be written as dn by or dny by dx raised to n at x equal to 0. So both have the same meaning. So therefore I can write yn 0 by putting just x equal to 0 wherever it appears in this. That gives me 1 by 2 times sin 0 plus n pi by 2. Okay, so this is the answer, and this depends on the value of n. Suppose we are required to find, say y, y3 of 0, y3 of 0 means we have to put n equal to 3 and in this formula. So y3 0 is 1 by 2 times sine 3 pi by 2. And what is the sine 3 pi by 2? It is minus 1. So final answer is minus 1 by 2. If you are asked to find y12, for example, so what is y12? y12 at 0. y12 at 0, you put n equal to 12. So y12 at 0 is nothing but 1 by 2 times sine of 12 into pi by 2. Okay, so 2 6 are 12. So sine 6 pi, and sine 6 pi is 0. 0 into something is 0. So y 12th derivative means 12th derivative of y at 0 is 0. So this way you can find some particular values of the derivative of the given order. Okay. In the next lecture, we are going to derive the antiderivative formula for the power of the binomial expression ax plus b. And then finally, one more result. It is about how to find the nth derivative of product of any two functions. And that is the most important result of our this first topic of successive differentiation. Okay, thank you.